Hey guys, today we're going to look at how to graph more complicated rational functions. But first we're going to start with just a simple one so that we can review a couple of things. So first of all, here we have this function f of x is equal to 1 over x minus 2. That is this graph here that we see. Now if we take the denominator and we make it equal to 0 and solve for x, we get that x is equal to 2. If you look at the graph, that's exactly where we have the vertical asymptote. So that is to say, which is what I have here, that you can find the equation of the vertical asymptote of a rational function by setting the denominator equal to 0 and solving for x. So that means that the equation for the vertical asymptote here is x is equal to 2. As long as you know the equation of the vertical asymptote, you can figure out the domain. The domain is going to be all real numbers except for this value, since that means that the graph will never touch that line. So my domain is going to be negative infinity to 2 union 2 to infinity. Now the range, as you can see here, we have a horizontal asymptote at y is equal to 0. And if you notice in the equation, we normally find the horizontal asymptote by seeing the number that is either added or subtracted at the end. And since there's no number, we can say safely that it's like plus 0. So we have that horizontal asymptote at y is equal to 0. So that means that the range, as long as you know your horizontal asymptote, you know what value you're going to exclude from the range, which in this case is 0. So my range is going to be from negative infinity to 0, union 0 to infinity. Now we're going to practice finding the equations of vertical asymptotes just based on the graph. As you can see here, these equations are not written in transformation form. And that's the whole point of this lesson, is we're going to see if we can figure out ways of graphing rational functions without having to rewrite it in transformation form. To find the equation of the possible vertical asymptotes, we noticed in the previous slide that we find those vertical asymptotes by setting the denominators equal to 0. So that's what we're going to do for these examples. So for the vertical asymptotes, we basically just ignore the numerator and focus on the denominator. So for this first one, to find the vertical asymptote, we set that denominator x minus 1 equal to 0. And we get that x is equal to 1, since we would have to add the 1 over. This is the equation of the vertical asymptote. That means that the domain is going to be all of the real numbers except 1. So negative infinity to 1, union 1 to infinity. Now we do the same thing here. We have x plus 1 in the denominator. So we're going to make x plus 1 equal to 0 and solve for x. Subtract 1 to both sides, we get that x is equal to negative 1. So this is the equation of my vertical asymptote. That means that the domain is going to be negative infinity to negative 1, union negative 1 to infinity. Now for these next two, in the denominator we have a quadratic. So we have to still do what we were doing before. We set the quadratic equal to 0. In order to solve this, we would have to factor. What we have here is a difference of squares. And how we factor that is we square root the first term, which is x. We square root the second term, which is 2. You make 1 plus and 1 minus and make it equal to 0. So that means that here we have two vertical asymptotes instead of one. We have x is equal to negative 2 and x is equal to positive 2 if you set each of these factors equal to 0 and solve for x. Now in order to find the domain, and I put it here, when you have multiple vertical asymptotes, you may find it helpful to create a number line with the excluded values in order to write out the domain. My two excluded values here are negative 2 and 2. So what I'm going to do here to write out the domain is I'm going to create a number line with those excluded values. My domain is all real numbers except for these two. So I'm going to use an open circle to indicate that these two numbers are not included, but everything else is included. By writing out your number line, it's a lot easier to see what the domain would be. The left side is negative infinity and the right side is positive infinity. So my domain is going to be from negative infinity to negative 2, not included, so I put a parentheses. Then I have this middle section, so I'm going to put u from negative 2 to 2. And then this last section here, so u 2 to infinity. So if you do your number line, however many shaded areas you have, that's how many intervals for the domain you will have. Now over here, we have x squared minus x minus 6 in the denominator. Same thing, you set that quadratic equal to 0, and we factor. The two numbers that multiply to give you negative 6 and add to give you negative 1 are negative 3 and 2. So my factors would be x minus 3, x plus 2. And we make each factor equal to 0. By doing that and solving for x, you would get here that x is equal to positive 3 and negative 2. So these are my two excluded values. So I'm going to create my number line here so that way I can figure out what my domain is. Always make sure that you put your numbers in order. Your domain is never correct unless it is in order. So we would put the negative 2 first and then the 3. I would exclude these two numbers, but everything else would be included in my domain. So the left side again is negative infinity and the right side is positive infinity. So my domain is going to be from negative infinity to negative 2, union negative 2 to 3, union 3 to infinity. Now, as you can see here in the chart, I put here possible vertical asymptotes. So this means that there could be something else instead of a vertical asymptote. So let's examine something called a hole. If you look here on the graph, we see that we have a vertical asymptote here at x is equal to negative 2. That is the equation of the vertical asymptote. A hole, however, is an open circle that is undefined on the graph, which is here. And we have a hole at x is equal to 3. Now, how do we find a hole? If I didn't have this graph, we would have to use the equation. How we find whether we have a hole or a vertical asymptote, what we have to do is factor both the numerator and the denominator completely. So let's start off with that. We have in the numerator 2x squared minus 3x minus 9. So let's focus with factoring the numerator first. In order to factor, we have this number in front of the x squared. If you ever have a number in front of the x squared that cannot be divided across the entire quadratic, then that means we're going to have to use the AC method. So let's start off with that. So we have 2x squared minus 3x minus 9. AC in this example is 2 times negative 9, which is negative 18. Then we have to figure out what B is going to equal to, which is when you have the two numbers that multiply to give you negative 18, but add to give you negative 3. The two numbers that multiply to give you negative 18 and add to give you negative 3 are negative 6 and 3. So now we take this quadratic and we rewrite it with b substituted for these two numbers. So we get 2x squared minus 6x plus 3x minus 9. Now we factor by grouping. 2x squared and negative 6x both have a 2x in common. And then we would have x minus 3. The 3x minus 9 has a 3 in common, so we would factor out a positive 3, and we would get x minus 3. So my factors here are x minus 3 and 2x plus 3. This is just the numerator. We also have to factor the denominator. The denominator is x squared minus x minus 6, and this can be factored to give you x minus 3, x plus 2. Since negative 3 times 2 gives you the negative 6, and negative 3 plus 2 gives you the negative 1. If you notice here, if you ever have the same factor in the numerator as in the denominator, you can cancel them. So I can cancel those x minus 3's. So that means that my simplified rational function is now 2x plus 3 over x plus 2. When we look here, in order to figure out what is the vertical asymptote, you have to look at the simplified version of the rational function. My vertical asymptote, if I take that denominator and make it equal to 0, we get that x is equal to negative 2. So this is the equation of my vertical asymptote, which you can see is what we got here when we just looked at the graph. Now the whole is found by looking at the factor that canceled. That is the factor x minus 3. And you make it equal to 0 and solve for x. If I add the 3, I get x is equal to 3. So that's where the whole is located, which is what we got here. So you can see that we didn't necessarily need the graph in order to figure out where there is a vertical asymptote and where there's a whole. And I have it here broken down for you as well. The graph of a rational function will have a whole when a factor of the numerator cancels out with a factor in the denominator. The whole is located at the x value that makes that factor equal to 0. So that's what we did here, the factor that canceled. I took it, I made it equal to 0 and solved for x, and that's the whole. The function will have a vertical asymptote when the denominator equals to 0 and it is not a common factor of the numerator. That's over here. This was still left in my denominator. So once you simplify your rational function, you look at what's left in the denominator, and that is what you set equal to 0 to solve for the vertical asymptote. So let's practice just that. We're going to focus only on vertical asymptotes, wholes, and domain. So just to reiterate here, most importantly, you only have a vertical asymptote if the factor of the denominator does not cancel out with the factor of the numerator. Wholes occur when the numerator and denominator have common factors, meaning that they are canceled out. And the domain of a rational function is affected by both the vertical asymptotes and the wholes. Both the asymptotes and wholes are excluded values of the domain. So let's start with this first one. We have x over x squared minus 4. So let's simplify this. The numerator cannot be factored, so we leave it as x. But x squared minus 4 is a difference of squares. So we factor that to be x plus 2, x minus 2. Since nothing will cancel out, that means that there are no wholes. We have two factors still left in the denominator. That means that we would set each of those factors equal to 0 and solve for x. Here I would have to subtract the 2, so x is equal to negative 2 is a vertical asymptote. Oops. And here I would have to add the 2, so x is equal to positive 2 is another vertical asymptote. So it's possible to have two vertical asymptotes. Now the domain. The domain is going to be restricted by these two vertical asymptotes. So we can put them on our number line here. My domain is going to be all of my numbers except for these two. So it's everything here on the left, in between, and on the right. So my domain is going to be from negative infinity to negative 2, union -2 to 2, union 2 to infinity. Now let's look at this next one here. We have g of x is equal to x plus 3 over x squared minus 9. Let's simplify this rational function. The numerator cannot be factored, so we're going to leave it as x plus 3. But the denominator, x squared minus 9, is another difference of squares. So we can factor that to be x plus 3, x minus 3. As you can see, we have x plus 3's here that repeat both the numerator and the denominator, so they can cancel, leaving me with a simplified rational function of, since there's nothing left in the numerator, we would write 1 over x minus 3. Now whatever you have left in the denominator that did not cancel, that's where you would have a vertical asymptote. So we have a vertical asymptote here at x is equal to positive 3. Because if you make x minus 3 equal to 0, you would have to add the 3 to the other side. Now the whole is when you set the factor that canceled, which is x plus 3, and you make it equal to 0. You would have to subtract 3 to both sides, so you have a whole at x is equal to negative 3. Now the domain. These two here are both excluded values. So to figure out the domain, you can put both of those numbers on your number line, always making sure that those numbers are written in order. We would exclude the negative 3 and the 3, but all the other numbers on either side and in between is okay. So that means that my domain is going to be from negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. Last one here. We're going to simplify this rational function. X squared minus 25 is another difference of squares, which can be factored to be x plus 5, x minus 5, and the denominator is just x plus 5. As you can see here, the x plus 5's will cancel. So we're left with, here in the numerator, x minus 5, and in the denominator, that's just 1, but we don't ever have to write over 1. So this is my now simplified equation. For the vertical asymptote, since we have nothing left in the denominator, that means that there are no vertical asymptotes. Since vertical asymptotes is only when you have factors in the denominator. However, we do have a whole because we have a factor that canceled. So we take that factor and we make it equal to 0. Subtract the 5, we get that we have a whole at x is equal to negative 5. Now the domain. Like I said in the previous ones, the domain is affected by both the vertical asymptotes and the wholes. So this whole here is an excluded value. So that means that my domain is going to be all real numbers except for negative 5. So my domain is going to be from negative infinity to negative 5, union negative 5 to infinity. Now that we know how to find the difference, or how to find vertical asymptotes and wholes and the difference between them, let's look at how we can find horizontal asymptotes just based on the graph. On the equation. So there's a couple of tricks that you can use here to figure out horizontal asymptotes. As a reminder, when we were looking at these rational functions that were in transformation form, we would look at the number that is added or subtracted at the end of the rational function in order to figure out what the horizontal asymptote is. However, these equations here are not written in transformation form. So that means that we're going to have to try to find another way of figuring out where there's a horizontal asymptote. Now, if your functions are written in this format, what you have to do is you're going to compare the degree of the numerator with the degree of the denominator. And there are 3 scenarios for that. As a reminder, the degree of anything is the highest exponent. So what we're comparing here is the highest exponent of the numerator with the highest exponent of the denominator. If the degree of the numerator is smaller than the degree of the denominator, then that means that there is a horizontal asymptote at y is equal to 0, always. So if you look here at this example, the highest exponent in the numerator is 1. The highest exponent in the denominator is 2. 1 is less than 2. So that means that we have that horizontal asymptote at y is equal to 0. Now, if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is equal to the value of the leading coefficients divided by each other. Let's look at this one here. The degree of the numerator is 1. That's my highest exponent. The degree of the denominator is also 1. So what we do is ignore everything else. We're just going to divide the coefficients that are attached to those x's. 4 divided by 2 is 2. So that's why we would have a horizontal asymptote there at y is equal to 2. Lastly, if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. So you see here that the degree of the numerator is 2, which is larger than 1. Since it is larger, that means no horizontal asymptote. So let's look at these examples here just to make sure that we understand. In the numerator, the highest exponent of x is 1, and in the denominator, it's 2. 1 is less than 2, so that means that we have a horizontal asymptote at y is equal to 0. For b, the degree of the numerator is 2, which is the same as the degree of the denominator. So what we do is divide the coefficients that are attached. 4 divided by 2 is 2. So we have a horizontal asymptote at y is equal to 2. In this last example, the highest exponent in the numerator is 3, and the highest exponent of the denominator is 2. 3 is larger than 2, so there is no horizontal asymptote. So you don't really have to do any real calculations. You're just comparing the highest exponent of the numerator with the denominator. So now let's put everything together and look at how to graph. Your first step when we're graphing is to find all asymptotes and holes. So let's start with the vertical asymptote. If I look at my function here, there is nothing for me to factor. So this is it. The denominator is x minus 2. That means that we have a vertical asymptote at x is equal to 2. Since nothing will cancel from the numerator and from the denominator, this means that there are no holes. To figure out the horizontal asymptote, we compare the degree of the numerator with the degree of the denominator. Here the exponent is 1, and here as well. Since both have an exponent of 1, we would divide the coefficients that are attached to the x's. Even though we don't actually see any coefficients, there's like an invisible one here and here. 1 divided by 1 is 1. So we have a horizontal asymptote at y is equal to 1. Just by having this information, we can figure out what the domain is and what the range is. The domain is going to be all real numbers except for where you have your vertical asymptotes and holes. We only have a vertical asymptote, so my domain is going to be from negative infinity to 2, union 2 to infinity. The range is affected by the horizontal asymptote. So it's going to be all real numbers except for y is equal to 1. So my range is going to be from negative infinity to 1, union 1 to infinity. Now let's start graphing. At the moment, I have at least my asymptotes. So we can go ahead and put that on the graph. We also have the horizontal asymptote, so I'm going to put that on my graph here as well. So we found all asymptotes and holes. Now what we're going to do is we need to figure out what my graph is doing on either side of the vertical asymptote. Am I going to have my curve up here or down here? Or am I going to have my curve here and here? So what we're going to do is we're going to create a table using x and our function. You are going to choose an x value to the left of the vertical asymptote and an x value to the right of the vertical asymptote. So since my vertical asymptote is at 2, I would choose x is equal to 1 and x is equal to 3. You could have also used 0 or -1. You can use anything that is to the left of the vertical asymptote and anything that's to the right of the vertical asymptote. I just usually like to use the points that are directly next to it. So now that I have chosen my two x values, in order to figure out the y values, we're just going to plug it into the equation and work it out. So we have 1 plus 1 divided by 1 minus 2. 1 plus 1 is 2, and 1 minus 2 is -1. 2 divided by -1 is -2. So that means that I have a coordinate at 1, -2. Now I'm going to do the same thing with 3, and I'm going to plug it into my function. So 3 plus 1 over 3 minus 2. 3 plus 1 is 4, and 3 minus 2 is 1. So that means that 4 divided by 1 is 4. So I have a coordinate at 3, 4. Now that I have my points, we're going to go ahead and put it on the graph. So we have 1, -2, and 3, 4. Based on where these points lie, we can now graph it based on those asymptotes. So my graph is going to curve downward on this side and upward on this side. So the process by graphing in this format is a little different. You have to find all of the information about the rational function first, and since it's not written in transformation form, we can't use our transformations. So we just choose x's, one to the left and one to the right of the vertical, and plug it in. Let's try another example. We have here f of x is equal to x squared plus 2x minus 3 over x squared plus x minus 2. So first, in order to figure out the vertical asymptotes and the holes, we would need to factor the entire equation. So that's what we're going to start off with. The numerator, x squared plus 2x minus 3, can be factored to x plus 3, x minus 1. Since 3 times -1 is -3, and 3 minus 1 is +2. Now we do the same thing for the denominator. X squared plus x minus 2 can be factored to x plus 2, x minus 1. Since 2 times -1 is -2, and 2 minus 1 is +1. By looking at my equation here, I see that I can cancel the x minus 1's. So my equation would read x plus 3 over x plus 2. This is now my simplified rational function. So my vertical asymptote is what's left in the denominator. I have an x plus 2. That means if I make it equal to 0, we have a vertical asymptote at x is equal to -2. Now for the whole. We have a factor that canceled out. So that means that we have a whole where that factor is equal to 0. So we take the whole, x minus 1, and make it equal to 0. Add the 1, we have a whole at x is equal to 1. Now for the horizontal asymptote. In order to figure out the horizontal asymptote, you can either look at the original function, or you can even look at your simplified function. If you notice, I'm just going to look at the original. The numerator has the highest exponent of 2. The denominator also has a highest exponent of 2. Since they are equal, that means that we divide the coefficients in front of that x. Even though we don't see them, it's as if there is an invisible 1. 1 divided by 1 is 1. So we have a horizontal asymptote at y is equal to 1. Now for the domain. The domain is going to be restricted by the vertical asymptote and the whole. Those are my excluded values. So if you would like, you can create your number line. These are the two values that I need to exclude, -2 and 1. So I'm going to use my open circles here, but everything else for the domain would be included. So my domain is going to be from -infinity to -2, union -2 to 1, union 1 to infinity. My range is affected only by the horizontal asymptote. So this is the value that I will exclude from the range. So my range is going to be from -infinity to 1, union 1 to infinity. Now we're ready to start figuring out our graph. Once you want to start putting things on here, we would start off by placing the asymptotes, just like before. So we have x is equal to -2 and y is equal to 1. The whole is going to be placed last. That is the very last thing that you do on your graph. We'll get to that part later. So now we need to draw these curves. So we're going to create our table of values. When you create your table, if your function is simplified, I highly recommend using the simplified version of your rational function when you're plugging in numbers. It's going to make finding the y values much easier than if you were to use the original version. Since I have my vertical asymptote here at x is equal to -2, I'm going to choose an x value to the left and an x value to the right. An x value to the left would be -3, and an x value to the right would be -1. So now we plug in these x's into the function. We would get -3 plus 3 over -3 plus 2. -3 plus 3 is 0, divided by -3 plus 2, which is -1. And 0 divided by anything is 0. So I have my first coordinate at -3, 0. If I plug in -1, I get -1 plus 3 over -1 plus 2. When I work this out, -1 plus 3 is 2 over -1 plus 2, which is 1. And 2 divided by 1 is 2. So I have another coordinate at -1, 2. So now we're going to put both of these points here on my graph. So we have -3, 0 and -1, 2. We can now draw our curves. But my graph here is not complete because of this hole. We have a hole here at x is equal to 1. So what we do is we go to x is equal to 1, find the function, and we're going to put an open circle there to indicate that that's where you have a hole. And I'm just going to go ahead and erase what's in the middle here. There we go. And there's my hole. Now this graph is complete. So what we've covered so far are vertical asymptotes, horizontal asymptotes, and holes. But there is one other kind of asymptote, which is a slant asymptote. also known as an oblique asymptote. Slant asymptotes are a little special. They only occur if there is no horizontal asymptote and the degree of the numerator is exactly 1 degree larger than the denominator. If that's the case, then the rational function has a slant asymptote. So let's examine this equation. We have x squared plus 1 over x minus 1. If you notice, the degree of the numerator is larger than the degree of the denominator, since it's 2 and here it's 1. If the degree is larger, that means that there is no horizontal asymptote. So that is your first clue. If you don't have a horizontal asymptote, then what you would do is you would compare the degrees and make sure that the numerator is exactly 1 more larger than the denominator, which 2 is exactly 1 degree larger than 1. So therefore, there is a slant. And how we find the slant is through division. So you can either choose to divide x squared plus 1 by x minus 1, either using long division or synthetic division. However, synthetic division is usually easier. So if we're dividing, think about it like this. We are doing x squared plus 1 divided by x minus 1. When we're using synthetic division, you have to decide what number comes here on the box. And that depends on this. Whatever number is added or subtracted to the x, you make it equal to 0 and solve, and you get 1. So basically just switch the sign of this number. Or you can just take x minus 1, make it equal to 0, solve, you get x is equal to 1. So that's what goes in the box. Then you write the coefficients of the numerator, which it starts with x squared, so that would just be 1. There is no x, so we put 0, and then the 1. Bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. Times 1 is 1, and we get a remainder of 2. Now, when you're finding the slant asymptote, the remainder does not matter. This is going to tell us what the slant asymptote is. If you remember when we were doing synthetic division, your answer is always 1 degree less than whatever you were dividing by. So that means that this represents 1x, or x, plus 1. This is the equation of the slant, y equals x plus 1. Then you are expected to be able to graph it on the graph. Now, it's already graphed for you, but I just want you to see how we would graph the slant, so that way we can confirm it with what's on the graph here. Remember that the equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept. So in this equation, 1 is the y-intercept. So that's why you see that the slant has a y-intercept of 1. Then here the slope, even though we don't see it, there's an invisible 1 there. That means that the slope is 1. Or you can say 1 over 1, since slope is easier to put on the graph if you have the fraction. And all whole numbers are always over 1. So again, as a reminder, slope is rise over run. So the numerator tells you how to move up and down, and the denominator tells you how to move side to side. Since it's 1 over 1, that means we would go up 1, right 1, up 1, right 1, etc. And if we continue, you can see how it lands all on this graph. So that's how you would find the slant. Let's now practice putting this all together. We have here x squared minus 5x plus 7 over x minus 2. And we want to be able to graph this. So first, I noticed that the numerator is a quadratic, and we would factor it if we can. I put there as a note in blue that if the numerator cannot be factored, then just leave it. If you notice here, the only two numbers that would multiply to give me 7 are 1 and 7, or -1 and -7, which none of those would add up to give me -5. So that means that this numerator cannot be factored. So we're going to leave it. And if it cannot be factored, that means that nothing is going to cancel with x minus 2. So if nothing cancels, that means that we have no wholes. But for the vertical asymptote, we have this x minus 2 in the denominator. That means that we have a vertical asymptote at x is equal to 2. For the horizontal, we look at the degree of the numerator, which is 2, and compare it with the degree of the denominator, which is 1. 2 is greater than 1, so there is no horizontal asymptote. But if you ever have no horizontal asymptote, you want to see, is it possible that we have a slant? The degree of 2 is exactly 1 more than 1, so that means that we do have a slant. So we are going to have to divide x squared minus 5x plus 7 by x minus 2. So we're going to use synthetic division. Whatever is in the denominator, you're going to solve for 0, which is 2, and put it in the box. Then we write the coefficients that are in the numerator. We have 1, negative 5, and 7. Bring down the 1. 1 times 2 is 2. Negative 5 plus 2 is negative 3. Negative 3 times 2 is negative 6, and we end up with a remainder of 1. But remember that the remainder is not going to do anything for our slant. This is what represents the slant. This is x, and this is the y-intercept. So we have a slant at y equals x minus 3. So now we're going to go ahead and put everything that we know so far on our graph. We have the vertical asymptote at x is equal to 2, and we have a slant at y equals x minus 3. So here the y-intercept is negative 3. So that's where I'm going to put my first point. My slope, even though we don't see it, is a 1. That means that my slope is 1 over 1. So I'm going to go up 1, right 1. And I would recommend you do this throughout the entire graph. So we're just going to follow this pattern. Up 1, right 1. All the way until I get to the very end on either side. Now, even though we have a slant, that's okay. We're still going to follow the same process as we did before. We're going to create a table of values. And we are still going to choose 2 points, one to the left of the vertical and one to the right of the vertical. Since my vertical asymptote is at 2, I'm going to choose 1 and 3. My equation was not able to be simplified, so we're going to use the original, which is x squared minus 5x plus 7 over x minus 2. So we plug in the 1 into the equation. We get 1 squared, which is 1, minus 5 times 1, which is 5, plus 7 over 1 minus 2. When we work this out, we get 1 minus 5, which is negative 4, plus 7 is 3, over 1 minus 2, which is negative 1. And 3 over negative 1 is negative 3. So we have a coordinate at 1, negative 3. Now we do the same with 3. 3 squared is 9, minus 5 times 3, which is 15, plus 7, all over 3 minus 2. Work this out. 9 minus 15 is negative 6. Negative 6 plus 7 is 1, over 3 minus 2, which is 1. And 1 divided by 1 is just 1. So we have a coordinate at 3, 1. So we're going to put these 2 points now on my graph. We have 1, negative 3, and 3, 1. Now, depending on where it lands, you're going to have to graph it based on those asymptotes. So you're going to curve along the slant and along the vertical. So it's going to look something like this and then curve down. Over here, since it lands also in the pocket, we're going to curve along the slant and then along the vertical. And this would be my graph. Let's try one more. We have here f of x is equal to x plus 1 over x squared plus 5x plus 4. And I have here as a note, will this graph have a slant asymptote, and how would you know? If you compare the degrees, the degree of the numerator is 1, and the degree of the denominator is 2. 1 is less than 2, so that means that we have a horizontal asymptote at y is equal to 0. So since the degree of the numerator is smaller, that means that no, we are not going to have a slant. And the reason is that because there is a horizontal asymptote. That's another thing. I mean, think about it. We only have a slant if there is no horizontal asymptote. They cannot exist at the same time. So because we do have a horizontal asymptote, that means that it is not possible for us to have a slant. Now let's get the rest of this information. In order to figure out if we have or where we have a vertical asymptote and a hole, we need to make sure that this function is completely factored. So let's simplify it. The numerator cannot be factored, so it's just x plus 1. The denominator, however, can be factored. The two numbers that multiply to give you 4 and add to give you 5 are 4 and 1. So my factors are x plus 4, x plus 1. The x plus 1's can cancel. So that leaves me with a simplified rational function of 1 over x plus 4. By looking at my simplified rational function, I can determine that I have a vertical asymptote at x is equal to negative 4, since that's what would make my denominator equal to 0. Since I had this factor here that canceled, in order to figure out the whole, you set the factor that canceled equal to 0, meaning that I have a whole at x is equal to negative 1. The domain of this function, remember, is restricted by the vertical asymptotes and the whole, since those are both my excluded values. So if you want to figure out the domain, if it's hard because there are two numbers, you can place them on a number line, always making sure that your numbers are placed in order. So we have these two that are my excluded values, but all my other numbers would be included in the domain. So that makes my domain from negative infinity to negative 4, union negative 4 to 1, negative 1, union negative 1 to infinity. The range is restricted by the horizontal asymptote. Since we have a horizontal asymptote at y is equal to 0, that means that my range is all real numbers except 0. So from negative infinity to 0, union 0 to infinity. Now let's graph. We can place the asymptotes on the graph. We have x is equal to negative 4 and y is equal to 0. Remember that the whole we're going to place last. So if you need to make a note so you don't forget the whole, either starring it, boxing it, go for it. Let's create a table. We have x, and then I'm going to use my simplified version of my rational function, which is 1 over x plus 4. I need to choose two x values, one to the left of the vertical and one to the right of the vertical. Since my vertical is located at negative 4, I'm going to choose negative 5 and negative 3. and now we plug it into my function. So we have 1 over negative 5 plus 4, which gives me 1 over negative 1, and 1 divided by negative 1 is negative 1. So I have a coordinate at negative 5, negative 1. Now I'm going to plug in the negative 3. 1 over negative 3 plus 4 is equal to 1 over 1. And 1 divided by 1 is 1. So that means that I have another coordinate at negative 3, comma 1. So now we can place these two coordinates on the graph. We have negative 5, negative 1, and negative 3, 1. Now we create the curves based on where it lands and those asymptotes. Now I'm going to come back here because we are missing the hole. The hole is located at x is equal to negative 1. So I go to my graph where x is negative 1 and I place my open circle. And that means that that is where I have the hole. And that's how you graph more complicated rational functions.